Hello, my name is Pablo Linares.
And my name is Markus Tempelmayr.
We both are PhD students of Professor Felix Otto at Max Planck Institute for Mathematics and the Sciences.
And today we want to present a joint work on a tree-free construction of the structure group.
Partial differential equations driven by random forces arise naturally in several branches of physics like quantum field theory. Such is the case of the dynamical phi-4 model and the parabolic Anderson model, both on the slide. One of the main challenges when understanding these models comes from the singular nature of the noise. In applications, Xi is a random distribution of very low regularity. The prototypical example is space-time white noise. Nonlinear equations driven by these random forces fail to even make sense. In this case, the distributional products phi to the cube and u times psi are not meaningful. Therefore, understanding these models requires first giving an actual meaning to the equation and then providing a solution theory. The analysis of singular stochastic PDEs has been a growing field in the past decade. One of the main contributions to this field is the theory of regularity structures developed by Martin Heijger. The core of Heijger's theory is the understanding that Taylor polynomials are not enough by themselves to describe local behavior of rough functions or distributions. The solution comes in the form of a generalized Taylor jet where we replaced the monomials by actual nonlinear functionals of the noise which depend on the structure of the equation to solve. The theory of regularity structures combines ideas from different branches of mathematics. There is an algebraic side, which consists on giving an algebraic structure to these generalized jets. There is a probabilistic step, which is actually in charge of giving meaning to these nonlinear functions of the noise by means of exploiting the probabilistic properties of the noise via renormalization. And finally, there is the more analytic side, which consists of developing a solution theory, first in the space of generalized Taylor jets via Schauder theory, and then associating to each jet an actual functional distribution in the classical sense in what we call reconstruction step. In the algebraic side, the main notion is the regularity structure. A regularity structure consists of three elements: a set of homogeneities, which indeed contains the homogeneities of the generalized monomials to consider, the model space, which is a graded vector space, which contains the algebraic structure for these generalized jets, and the structure group G, which contains the recentering maps. By recentering, we mean that we change from the local description around a given base point x to the local description around a different base point y. This recentering is very easy in polynomials, where it's just encoded by the binomial formula, but extending it to the generalized monomials is non-trivial and requires ideas from Hopf algebras and representation of groups. The construction of the structure group is the main topic of this video. The approach that we will present is designed with the example of a quasi-linear equation in mind. In quasi-linear SPDEs, the distributional products are inside the differential operator. Our approach differs from that of Heijger in the sense that we replace his tree-based approach, inspired by the theory of branch graph paths, by a greedier multi-index description. Ultimately, this implies replacing combinatorics of trees by more Lie geometric arguments. We invite you to check our paper on the archive. You will find a link in the description of this video.
Let's start our construction with some motivation. Consider the ODE dtu equals a of u times some driver xi with homogeneous initial data. The philosophy that will guide our whole construction is that we consider all nonlinearities at once, and hence we see the solution u not only as a function of time, but also as a functional of the nonlinearity a. This way, although it seems that we only consider the homogeneous initial value problem, we recover the whole solution manifold by simply shifting the nonlinearity a. More precisely, consider the solution u to the ODE with nonlinearity shifted by a real number u0 and add to the solution this same number u0. Then this function, here denoted by u tilde, solves the ODE with nonlinearity a and takes the initial value u0. Moreover, we are able to recenter in the following sense. Consider again a solution to the ODE with shifted nonlinearity and add the same shift. But this time, the shift, here denoted by pi, is allowed to depend on the nonlinearity A. Then we again recover a solution to the ODE with nonlinearity A, but for a suitable choice of the shift having initial value 0 at time 1. Moving on to the PDE we are interested in, one big difference is that the solution manifold is no longer one-dimensional but infinite dimensional. Therefore, we think of the solution manifold as being parameterized by space-time polynomials P, and we see the solution U to be a functional of the nonlinearity A and the polynomial P. In the same way as for the ODE, the constant part of the polynomial can be encoded in the nonlinearity A, and hence we only consider polynomials modulo constants. Therefore, we fix the polynomials to vanish at the origin. The goal is now to find a group with representation that encodes this recentering in the case of the PDE. At the core of the construction are the following actions. As already seen in the motivation, the shift of the nonlinearity plays a crucial role when recentering. Therefore, consider the map that shifts the nonlinearity and keeps the polynomial fixed. We lift this map to the space of functions on pairs AP and consider its infinitesimal generator, which we denote by D0. Next, consider the map that keeps the nonlinearity fixed and tilts the polynomial P by a monomial xn, where n is different from 0. We again lift this map to the space of functions on pairs AP and denote the infinitesimal generator of this action by dn. Last, we have to consider the shift of space-time, which means that we want to shift the polynomial by a space-time vector. But once the polynomial is shifted, it does no longer vanish at the origin. To fix this, we just subtract the correct value of the polynomial, and to not lose any information, we shift the nonlinearity by the same value. This gives rise to the infinitesimal generators partial 1 and partial 2. However, as already mentioned earlier, we also have to consider shift of U-space and tilt by polynomial that depends on AP. To this end, we introduce coordinates on AP space. We denote the kth Taylor coefficient of A by zk and the nth Taylor coefficient of the polynomial P by Zn. This naturally gives rise to multi-indices gamma and allows to define the monomial Z gamma, which we see as a function on the pair AP. Having this in mind, we redo the construction of the generators D0 and Dn, but this time with coefficients that depend on AP. This leads to the infinitesimal generators Z gamma Dn. Hence we have our building blocks, namely the elements partial 1, partial 2 and Z gamma Dn. Let me also mention that the multi-indices gamma allow to rewrite the solution U, at least formally, in a power series in the monomials Z gamma, where the coefficients pi gamma collect the partial derivatives of the solution U with respect to the coordinates Zk and Zn. In the abstract framework, it is also necessary to not evaluate this power series at AP, which we then call the model pi. Since not all model components pi gamma give a contribution to this power series, the model pi lives in a subspace of the power series, which we denote by T star, and indeed is the dual of the model space T. We now come to the algebraic structures. Since our building blocks are derivations on power series, they naturally come with a pre-Lie product given by the covariant derivative of vector fields. Unfortunately, the span of our building blocks, which we denote by L, is not closed under this pre-Lie product. However, the pre-Lie product gives rise to a Lie bracket, under which L is closed, and therefore we obtain a Lie algebra. This Lie algebra in fact is graded, and the grading is strict positive. Moreover, all elements in the Lie algebra are strict triangular with respect to the homogeneity of the regularity structure. This grading and triangularity are the essential ingredients to obtain finiteness properties that we need later.
Once the Lie algebra is defined, we start a completely algebraic path towards the structure group. The first step is to consider the universal envelope in algebra, which is the tensor algebra over L factored by the commutator given by the Lie bracket. This universal enveloping algebra carries a natural structure. It is a Hopf algebra where the product is given by concatenation and the coproduct is characterized by its action on the elements of the Lie algebra and then extended to the whole space by compatibility with the product. The space L is actually a space of derivations, and we can think of U of L as a space of endomorphisms. However, we want to dissociate this identification and rather consider U of L as an abstract space of words together with a representation row which maps each of these words to the actual endomorphism. The representation is made in such a way that the concatenation of words in U of L yields composition of endomorphisms. Let us now discuss how we choose a basis in the space U of L. By Poincaré-Birkhoff-Witt theorem, it is easy to choose a basis which is just produced by concatenation of elements of the Lie algebra. However, to obtain linear independence, we require a non-canonical choice of an ordering in the set of generators of the Lie algebra. Our pre-Lie structure allows us to split a generator Z gamma dn into the multiplication part Z gamma and the derivation part dn. This allows us to define elements like the one on the slide, where all the z's are put to the left and all the d's are put to the right. Note that the z's and the d's commute among themselves, so an element of this form does not require a specific choice of an ordering. Indeed, these elements form a basis which we denote by djm, where j is a multi-index over the set of pairs gamma n, and m is a multi-index over the set 1, 2. The normalization constant j factorial m factorial is taken in such a way that the coproduct acquires a trivial representation with respect to these spaces. We now turn to the more technical part of dualization. We consider a space T+, which is linearly isomorphic to U of L with a basis given by ZJM, and establish a canonical duality pairing between the basis of U of L, djm, and the basis of T+. By dualization, the coproduct in U of L turns into a product for T+, which thanks to a trivial structure is nothing but the polynomial product in T+. The concatenation product and the representation row yield a coproduct and a comodular structure respectively. However, in an infinite dimensional context as ours, these two maps are not well defined in general. In our construction, they do depend on finiteness properties which we obtain thanks to a gradient structure in the Lie algebra and due to the triangularity of these endomorphisms. After overcoming this technical difficulty, we can claim that T+ is actually a Hopf algebra and the model space T is a left comodule over T+. Such are the main assumptions in high-res algebraic construction. Moreover, we can recover high-res intertwining property between delta and delta plus. In our case, Jn arise by transposition of injections of the universal envelope in algebra onto spaces of the Lie algebra L. The rest of the construction is well known in the theory. We consider multiplicative functionals over the space T+, which carry a group structure given by the so-called convolution product. This convolution product comes from delta plus, the coproduct of T+, and therefore is nothing but an extension of the concatenation product in U of L. We then transfer this group structure to the space of endomorphisms thanks to a comodular structure delta. This group of endomorphisms is actually a structure group, and the appropriate choice of the multiplicative functionals yields the desired recentering properties.
Let's revisit the construction of the structure group in the simple example of the ODE we considered for motivation. Since there are no polynomials needed, the only action we have to consider is the shift of the nonlinearity with its infinitesimal generator Z gamma d0. The span of these building blocks gives rise to the Lie algebra, which in this case is even a pre-Lie algebra. Note that the Lie algebra as a linear space is isomorphic to the model space T. The Lie algebra also gives rise to the universal enveloping algebra, where the basis elements take now the simpler form of first the Z gammas, then the dn's. The space T plus that arises from the pairing with U of L is now just a polynomial algebra indexed by multi-indices gamma, and therefore, as a linear space, again is isomorphic to the model space T. T plus, as a Hopf algebra, is equipped with a coproduct delta plus, and finally gives rise to the structure group G. Summarizing, we have equipped the space T with a lot of different algebraic structures. Finally, we want to make a connection to the existing literature on branch graph paths, still for the same ODE. As already mentioned, the model components pi gamma collect the partial derivatives of the solution U with respect to the monomials with respect to the coordinates zk and zn. Therefore, by taking derivatives of the equation, we obtain a family of ODEs for the model components pi gamma. For example, taking gamma equals E0, we see that the derivative of pi E0 equals the driver psi. On the other hand, in the existing literature, the model is recursively defined in terms of trees. Here, B plus of tau 1 up to tau k denotes the following tree. Consider tau 1 up to tau k, attach a new edge to the nodes of each of them, and merge all these new edges into a common root. As the examples given here suggest, there is a connection between the two models. Namely, the model component pi gamma always equals a linear combination of the x taus, where the linear combination is built of all trees tau, having for every k exactly gamma of k nodes with k children. The factors in this linear combination are related to some symmetry properties of the trees. The relation between these models naturally gives rise to a dictionary between the model spaces. Namely, a monomial Z gamma is mapped to the same linear combination of trees tau. Here, we see an example where a monomial Z gamma is indeed mapped to a linear combination of trees. This shows that our index set of multi-indices is more parsimonious than the usual index set of trees. We now want to make a connection between the algebraic structures on both sides. On our side, the Preely product between a monomial Z gamma 1 and Z gamma 2 is given by applying D0 to Z gamma 2 and then multiplying the result by Z gamma 1. On the classical side, there is the Grossmann-Larsen-Preely product, which is given by grafting of trees, though with different factors. Namely, one counts how often a tree can be cut to obtain the corresponding trees. By comparing the two Preely products, we clearly see that we replaced the combinatorics of trees on the classical side by Lie geometry on our side. However, both worlds are connected in the following sense. The transposed map of the dictionary phi is a Preely morphism between our structure and Grossmann-Larsen's. Hence, because the model space T can be identified with T+, the dictionary phi is a co-algebra morphism, meaning that first translating a multi-index into trees and then cutting with Kohn-Kreimer's coproduct is the same as first applying our coproduct to a multi-index and then translating into trees. This result holds not only true for the ODE, but also for semi-linear SPDEs, where the connection is no longer made to the coproduct of Kohn and Kreimer, but to the one defined by Heire and co-authors in their series of works on SPDEs.